Hello, in this video we are going to look at Hele-Shaw flows, which are a trick designed for experimentalists to generate the two-dimensional flows. We're going to see how the flow becomes two-dimensional. So Hele-Shaw flows are flows that are located within a Hele-Shaw cell, and a Hele-Shaw cell is just a very simple experimental trick that allows to simplify the fluid dynamics. So a Hele-Shaw cell looks like this. So we have a flat surface here, a two-dimensional surface, and with a very small gap under it, we place another of these surfaces. Okay? And the idea is the fact that the flow is going to happen in between these two plates, and this distance here, which I call h, is going to be very small compared to typical variations in the two other directions, which I'll call L. So my axes here are is as follows. So I'm going to have ex here, I'm going to have ey here. So my in-plane directions are x and y. The flow is going in the x or y direction, and that vertical direction or pseudo-vertical direction is ez, the one that is wall normal. And as I said, the trick here is to make sure that h is small enough such as h over L is small compared to 1. L being the natural length scale of the flow in these two directions, in the flow directions. In what follows, I'm going to call this quantity, because it's a small quantity, I'm going to call it epsilon. Okay, so Hele-Shaw flows are typically small Reynolds number flows, and therefore the starting point for such an investigation is to write down the Stokes equations. So the Stokes equations write as follow. I'm going to just write it down in 3 dimensions, but as you can see, x and y are going to be pretty much the same all throughout. So it's going to be mu d2u by dx squared plus d2u by dv squared plus d2u by, sorry, that's a y squared, d2u by dz squared equals dp by dx. Mu d2v by dx squared plus d2v by dy squared plus d2v by dz squared equals dp by dy. And in the z direction, we're going to have mu d2w by dx squared plus d2w by dy squared plus d2w by dz squared equals dp dz. So these are my Stokes equation. I'm going to get back to them in a moment, so I'll label them 1, 2, and 3. And I'm obviously going to complement this with the incompressibility condition. And the incompressibility condition gives me in 3D that du by dx plus dv by dy plus dw by dz equals 0. That's my equation number 4. And whenever we solve for a Hele-Shaw flow, pretty much all the time there's no special treatment that is made to these two walls. And therefore we're going to have a no-slip boundary condition at the walls. So we're going to have the following boundary conditions. Well, we are going to have at z equals 0 or h, well, nh, sorry, the 0 being the bottom and h being the top wall. We have that the velocity has to vanish. Okay, u equals 0. Okay, so well, I forgot to mention that what is typically done in these Hele-Shaw flows are to look at, for instance, the flow in a porous geometry, or when you have a T-junction, how the fluid for instance, is going to distribute between the two or more new paths that are open to it. We could be also looking at the flow past an obstacle, looking at various sorts of configuration related to this. But the key point here is that we want to isolate as much as possible the flow around, say, this geometry. Hence the need to get rid of that third dimension. Okay, so the first step to understand how how the flow becomes two-dimensional is to look at effectively to look at the non-dimensionalization. So let's proceed. And so we have a certain number of quantities to non-dimensionalize here. Let's start off by the position. So x, well, as I said, the natural length scale is capital L, so I'm going to non-dimensionalize it by capital L. The same thing can be said for y. And for z, in this case, we do have that natural length scale, which is h. And h is effectively epsilon times L, okay? So I am going to non-dimensionalize z by epsilon capital L. And what you see is going to happen is that variations in the z directions are going to be small. They're order epsilon. And therefore, spatial derivatives in the direction z are going to be large. Well, d by dz is homogeneous to 1 over epsilon L, right? So it's going to be of the order of magnitude of epsilon to the minus 1. That is to say, spatial derivatives in the z direction are going to be large. And that's going to be a key factor in what follows. We can also continue in saying that the velocity u has to be capital U star, where capital U is a velocity scale. V, well, you know, V and U, X and Y have the same sort of geometrical constraints, so there's no need to think that the scale in the velocity in the Y direction is going to be different from that in the X direction. And lastly, W is going to scale differently. I'll say, for now, I'm just going to write capital W, and I just wanted to add that the pressure also is going to scale in a particular fashion, and it's capital P, which is to determine later. Okay, so we do have all these assumptions here. Of course, W is to be determined, and of course P is to be determined. Okay, but we'll get to that in a second. Okay, so the first step is to determine these quantities. So for this equation here, the incompressibility constraint, if we non-dimensionalize it, gives us that u over L du star by dx star plus u over L dv star over dy star plus W over epsilon L dW star over dz star equals 0. And in other words, if I want to keep my flow, my three-dimensionality of the flow, I would have to have W scale like epsilon u, okay? So W equals epsilon u. This is a prerequisite from this equation, and otherwise either these terms or this term dominates. So that's my first quantity that is determined. And the other thing that we can do here is look at equations 1, 2, and 3. So first of all, let's just to determine the scaling for the pressure, capital P. So before doing this calculation, we first need to think that these terms here, the three of them, I don't have to look at the three of them. In fact, I know that d by dx squared is going to scale like 1 over L squared. D by dy squared is going to scale like 1 over L squared. And d by dz squared is going to scale like 1 over epsilon squared L squared. okay? And in the denominator, it's the same quantity, it's u. In other words, these are going to scale like u over L squared, and this is going to scale like u over L squared times epsilon to the minus 2. In other words, this is large compared to these two terms. And because it's large compared to these two terms, I can just neglect these two and simplify my first equation by just keeping the dominant term in the left-hand side, which is mu d2u by dz squared. And my right-hand side, so far I do not know anything about it. It's going to be this quantity. Okay, let's just have a look at the non-dimensionalization there. So that gives me that on the left-hand side, mu u over L squared, and it's epsilon to the minus 2 here, d2u star by dz star squared. And on the right-hand side, I've got p over L dp star over dx star, okay? And based on this, I can deduce a scale for the pressure, which is that P has to scale like mu u over L epsilon to the minus 2. That tells me that the pressure is large. I can carry out the same calculation for equation 2, but you will realize that x scales like y, and that u scales like v, so that equation is essentially going to give me the same result. So that's p scaling like mu u over L epsilon to the minus 2. However, the third equation might not give me the same result. So let's have a look at it. That third equation, first of all, the same reasoning for the left-hand side holds. That, well, these are the same in the denominator, but the numerator is different. And d by dz is larger than d by dy and d by dx. Therefore, I can simplify equation 3 by only keeping the dominant term in the left-hand side, and this dominant term is d2w over dz squared equals dp dz. And based on this, then I can non-dimensionalize this. So remember, w is epsilon times u. So I'm going to have mu u over L squared. There's epsilon to the minus 2 that comes up. So that's epsilon minus 1 here. d2w star over dz star squared. And on the right-hand side, I've got dp by dz. dz makes an epsilon appear. So I've got p over L epsilon to the minus 1 dp star over dz star. Alright? And in other words, from this equation I get the following scaling for the pressure, that it's going to be like mu u over L. Alright, so I've got 5 here, no that's not here, I've got 5 here and 6 here, which are my two different scaling for the pressure. Of course, they're different by a certain order of magnitude, epsilon squared. And of course, we cannot take the smaller of these two scales, because that small scale doesn't include the large one. And therefore, we have to say that it is the large one that we're going to take. So the pressure, so that's 5 and 6. Imply that the pressure scaling is P equals mu u over L epsilon to the minus 2. Alright, and based on this, well, now that we can set these into equations, well, that's 1, 2, and 3, we can find what the resulting system, what the leading order terms are in the resulting system. So for equation 1, we had deduced this, and this is the scaling that we chose. So these two terms are going to be in balance. So equation 1 gives me that d2u over dz squared equals dp dx. I'm going back to dimensional quantities here, just to see the equations in their dimensional form. Equation 2 was, serving pretty much, was having the same balance than equation as equation 1. So I'm going to have d2v by dz squared equals dp dy. And equation 3 is the one that we've written here. It would be in balance if we had, these two terms would be in balance if we had a pressure scaling like this. But remember that the pressure is actually larger than this. And that means essentially that if I plug in this scaling into this equation, this term is going to dominate above compared to this one. So the epsilon to the minus 2 here means that this is going to be epsilon to the minus 3 versus epsilon to the minus 1. Epsilon to the minus 3 is much larger. So that third equation is essentially just a condition for the pressure, and it is that dP by dZ equals 0. Okay? And we can write the incompressibility condition if we want. Okay, so the incompressibility condition would write du dx plus dv dy plus dw over dz equals 0. All right. So this is an interesting point here, is that we've reduced our equations. P does not depend on z, right? So we can take these two equations and integrate them. So if we integrate, so I'm going to write down that's going to be 7, 8, 9, and 10. So I can take 8 tells me that P is not a function of z. And in that case, I can take 7 and 8 and integrate them. So 7 gives me that u equals 1 over 2 mu dp dx z squared plus k1z plus k2, where k1 and k2 are constants of integration that may or may not depend on x and y. And now we can apply the boundary condition, and we need to see that the velocity is 0 at z equals 0 and z equals h. So in other words, k2 equals 0 and k1 has to balance here, so that at z equals h we get 0. So the boundary condition imply that u equals 1 over 2 mu dp dx, and this is going to be hz minus z squared. I'm introducing the minus here because the velocity goes against the gradient of pressure always, and the fluid flows from the high pressure regions to the small pressure regions. Therefore, I'm introducing this minus sign here that's going to make it a bit more tractable, or a bit nicer to understand. Okay, so that's for u. Well, the same equation here, it's the same problem for v, so equation 8 will give me, oh, that was 9 here, that was not 8, that was 9. So equation 8 will give me that the velocity in the vertical position, in the y direction, writes in the same fashion, so it's 1 over 2 mu times dp by dy, so hz minus z squared. So once that we've determined the velocities in the u and y direction, the x and y direction, as a function of the pressure gradient, remember in these flows it's the pressure gradient and perhaps some internal boundaries that are going to determine the flow. What we can do is actually look at equation 10, the incompressibility condition. And in fact, there is a trick that will allow us to understand how these flows, well, the physics behind these flows. And the trick on the equation 10 is to actually look at the fact that, trying to get rid of this z dependency of the flow. And one way to do this is to integrate over that distance to have, say, the average value over z. So I'm going to define the operator this operator, which means the average over z, That means that I'm going to take 1 over h because my z domain is of extent h. And then I'm going to integrate from 0 to h that quantity dz. All right? So it's simply an averaging operator. And I'm going to average equation 10. So 10 gives me the average of du dx over z plus the average of dv dy over z plus the average of dw over dz over z equals 0. So this integral over z commutes with the spatial derivative over x because, well, x and z are not linked. These walls are parallel and in particular they're orthogonal to the z direction. So these operators commute. So what that means is that this is, I'm going to write down that this is du bar, and I'm going to, let's define also that the average of u over z is denoted u bar, okay, just to simplify the notation, and similarly for v and w. So that's going to be du bar over dx. This equation, this term is essentially treated in a similar fashion because y and x do not depend on z. So these operators commute. I've got dv bar by dy. And it's interesting here. What I'm doing is integrating dw by dz over z, which means I'm looking at the value of w at h minus the value of w at 0. And the whole thing divided by h, of course. Turns out that if I look at my boundary conditions, the w has to be 0 at both the top and the bottom boundary, which means that this averaging process gets rid of that term. And what we're left with is an incompressibility condition in 2D for the average flow in the vertical direction. So remember that you had that three-dimensional flow with this very narrow gap between the two walls. Instead of looking at this flow, think about it as an average flow over that narrow gap. What you essentially have is a two-dimensional flow on this plan form. Okay, so because we've written this in this fashion, then we can also introduce an operator. Maybe that's going to be a bit more complicated for the notation, but I can write down that this is nabla parallel dot u bar equals 0. Okay, where nabla parallel is, well, the restriction of the nabla operator onto the parallel directions to the wall. That is to say, it's d by dx ex plus d by dy ey. There's no d by dz in there. And u bar and u bar vector is just the averaged quantities for the velocity. That's just a reduced way of writing this. Interestingly, from this, we do have equation 11 and 12 here. Okay, this is the definition for the velocity. We can do the same treatment. We can apply the same treatment onto these definitions for the velocity, and integrating u over z with boundaries of integration 0 and h, and then divided by h. And to get the averaged velocity, so that's u bar, and u bar is going to be minus 1 over 2 mu h dp dx. Okay, none of this depends on z, all right, so that we can just take everything out of the integral, times the integral from 0 to h of z h minus z dz. So that's going to give me z squared over 2. That obviously only take values, non-zero values for the top boundaries. So that's h cubed over 2, and that's going to be h cubed over 3. 1/2 minus 1/3 is 1/6. So what I get out of this is 1/6 of h cubed. In other words, I get minus h squared over 12 mu dp dx. Okay, and that simplifies dramatically my expressions, and particularly what that tells me is that the velocity is proportional to the pressure gradient, but also to the heights, well, the average velocity, or in other words, you know, that can be related to the flux, is also proportional to the square of the heights and to the inverse of the dynamic viscosity. These are important quantities to relate to the flow. And then I can obviously write that 12 in a similar fashion will yield that V bar is equal to 1 over 12 mu dp by dy. Sorry, there's an h squared here. Right? And that gives us, and I'm sorry about this, but I'm going to have to turn the page. And so I can write down that as a summary from this calculation, that the velocity averaged, okay, and I'm taking this vector here, is going to be equal to minus h over 12 mu, it's an h squared once again, and this is the gradient of pressure that we have, but restricted to the parallel directions, which is the operator that I've introduced here, times the pressure. Okay, so in a reduced form, I can write this out, right? And I can do even better, because h and mu do not depend on the position in our domain. So I can write down that this is in fact the gradient perp, right, so nabla perp, of minus h squared p over 12 mu. In other words, that the flow averaged in the vertical direction is a potential flow, right? So the flow averaged in the wall normal is a potential flow. Of potential, and this potential, I'm going to write it phi bar. I'm just writing a bar here just to remember that we're talking about quantities that are averaged in vertical direction, but this is just a notation for us to remember. And this potential is minus h squared p over 12 mu. And that's how essentially one can relate these Hele-Shaw flows to a dynamics that is exclusively two-dimensional by averaging over this vertical direction, right? So we set up with a fully three-dimensional flow, making only the assumption that this gap was very small compared to the extent over which the flow develops in the x and y direction. We've also said that the Reynolds number was small, which is not completely incompatible with the fact that h is a small quantity. And then we looked at the dominant terms and found out that the resulting equations, if we average them over z, we're reducing to a much simpler problem, which is this two-dimensional problem for which we have incompressibility in 2D for the average quantities and a potential flow for the average quantities in the x and y directions. Alright, so in this video we've looked at Hele-Shaw flows, and we've looked at how their three-dimensional set of equations, the three-dimensionality of the problem, can be reduced to a set of two-dimensional equations. This is a nice simplification that allows to make flows simpler in the context of experiments, and the theory is fully provided here. This concludes this video on Hele-Shaw flows.